A steel ball tears free from a magnet, races down a metal tube, and bridges two electrical contacts. 20 milliseconds later, an explosion of nitrogen gas inflates an airbag before your head reaches the steering wheel. This same ball sits silently through potholes, curb hits, and slammed doors. It never fires by accident. That's the engineering mystery we're about to solve. Here's the problem. The inflator takes 20 to 30 milliseconds to generate gas once triggered, which leaves the sensor only 10 to 20 milliseconds to decide if a crash is life-threatening. The airbag needs to be fully inflated before your upper body reaches the steering wheel, and a few milliseconds late means the cushion is useless. But normal driving constantly shocks the car. You hit potholes, strike curbs, and slam doors that a crude sensor would read as a crash. A sensor that reacted to every sharp force would fire during harmless events. That'd waste the bag when you need it most, and the explosion itself could injure you. In the 1950s, early inventors like John Hetrick tried compressed air systems, but they lacked a reliable way to distinguish a real crash from a hard bump. Alan K. Breed solved this in the late 1960s with a sketch on the back of an envelope. It showed a steel ball inside a metal tube held by a magnet. That simple drawing became the first practical crash sensor, but the real genius is in how the tube filters out fake crashes. Now, let's strip away the casing and look inside. A small steel ball rests in a metal tube, and in many designs, it's gold-plated. A permanent magnet at the rear end holds it firmly in place. When the car moves at a steady speed, the ball and the tube share the same motion, and the magnetic force is stronger than any gentle vibration from the road. Now imagine a severe frontal crash. The car's front end crumples, and the sensor housing slows down violently. But the ball has inertia, so it wants to keep moving at its original speed while the tube stops. The magnet fights back, but if the deceleration is strong enough, the grip breaks and the ball lurches forward. The ball travels roughly 7 millimeters down the tube and touches two spring-loaded electrical contacts. When the ball bridges them, the circuit closes and current flows instantly. There's no debate and no delay. The contact is pure physics. The gold plating isn't decorative. Gold resists corrosion better than silver or copper, so the contacts stay clean after years of heat and vibration. A dirty contact could mean a failed airbag, which is why the gold layer matters. Engineers tune the system by choosing the ball's mass, the magnet's strength, and the gap to the contacts. You won't find microchips or code inside. The sensor works as a mechanical computer using mass, magnetism, and distance. This is where the ball proves its worth. The real test is whether it can tell a pothole from a pole impact. Let's walk through 3 different crashes. First, a curb hit. The wheel strikes concrete, and the car feels a sharp spike of deceleration. The ball lurches forward, but the jolt is brief, and the force drops before the ball travels the full 7 millimeters. The magnet pulls it back. The contacts stay open, so the airbag stays silent. But a real crash looks completely different. Second, an offset crash. The front corner hits another vehicle or a barrier, and the crumple zone collapses over tens of milliseconds. The ball breaks free, rolls the full distance, and bridges the contacts. Current flows, and the airbag deploys exactly when it should. Third, a pole impact. A narrow object hits the front center, and the deceleration hits hard and fast. The ball tears free almost instantly and closes the circuit. The sensor fires at maximum speed because the danger is maximum. The clever part is how the ball acts as a physical filter. It doesn't react to peak force. It reacts to force built up over time and distance, and only sustained deceleration above roughly 2.5 G will carry the ball across the gap. That threshold is what separates a pothole from a crash. Once the ball bridges the contacts, the rest is mechanical inevitability. Current flows through the closed circuit to an electric match called a squib inside the inflator. The squib heats up and ignites in 1 to 2 milliseconds. That small flame lights the main propellant charge, which burns chemicals like sodium azide to generate nitrogen gas fast. The gas rushes into the fabric bag and inflates it in roughly 20 to 30 milliseconds. Small vent holes let the gas escape as your head presses in, so the cushion absorbs your motion without acting like a stone wall. From the moment the crash begins to full inflation, the entire sequence takes about 40 to 50 milliseconds. The average occupant's head doesn't reach the steering wheel for 60 to 80 milliseconds. The ball bought just enough time to put a soft cushion between you and the dashboard, and that cushion is already deflating as you hit it, so it absorbs your motion. The ball did its job for decades, but cars eventually needed sensors that could watch every direction at once. Modern vehicles use tiny silicon chips called MEMS devices that sense deceleration. They run software that filters noise and integrates force, but they follow the exact same logic as the ball. The ball and tube was the analog brain that proved the concept, and modern sensors are just digital versions of the same filter. Alan K. Breed's company supplied tens of millions of these mechanical sensors by the mid-1990s, and NHTSA estimates frontal airbags have saved over 50,000 lives in the United States alone. Sometimes the simplest physical solution lasts the longest. The hidden logic inside the machines around you is everywhere once you know how to look. Every drive you take depends on mechanical decisions made in milliseconds by parts you'll never see. If you want to see more of how the world really works, hit subscribe, and we'll see you in the next breakdown.